to begin with, I would like to what is the meaning of non-additivity. In doing this, I will recall a little, somewhat, what is known for additive systems. It is something that for sure you have learned in your general courses, and maybe it is something trivial for you. I mean, but it is better to recall this matter just to then later to see the differences with what happens in non-additive systems. So let me begin. So what is additivity? It is very simple, and so in this matter, both physics and mathematics are, let's say, quite simple. So we have, let's say, we have a macroscopic system, and let's imagine to divide it in two regions. This system has an energy E. So now, if you consider the terms in the Hamiltonian that involve only particles in this part of the system, you will have an energy E1. If you consider the terms in the Hamiltonian that involve only particles in this part of the system, you have energy E2. Then, if you now consider the final part of the Hamiltonian, the one that involves both particles which are in both part of the system, so maybe one particle here and the other particle here, you have a final, let's call E interaction. And obviously you have this. But now the point is the following. What does E interaction come from? Since we are talking about, in this case now at the beginning, we are talking about additive system, that means a short-range system, and practically they are synonymous. E interaction comes only from the particles which are near the edges of the separation. So the important point is that if you do this ratio and you send the number of particles to infinite, you get 0. This is basically the main physical fact that distinguishes a long-range system and short-range system, which in turn means additive and non-additive systems, because this thing for long-range system is never valid. Doesn't matter how large you make your system, it will never be true, because this particle will always interact with this one, because it is a long range. So while in a short range, you can say that E, when the system is large enough, is this one. You neglect the interaction. For long range, this is not true. And this is the main physical reason for all the differences, practically. This is for all the differences that you find both in the equilibrium properties and in the dynamical properties of between the two classes of systems. So the approach to equilibrium is different. The equilibrium properties are different. The kinetic equations that describe the approach to equilibrium are different, and so on, all this. Oh, by the way, I will focus on static properties, equilibrium properties. I don't know if there is time. I will touch just one issue concerning dynamics, but at the end of of my second lecture. But I have to see if there is time. Otherwise, I will focus, as I was planning, just on equilibrium properties. So this additivity has another important consequence, which is extensivity. So from this one, from this equality, of course, you can iterate for any small part of the system as long as it is macroscopic. But this means the following, that if you take the energy of an n-particle system, and first let me write, where is it? The eraser? Thank you, thank you. First, let me write the energy as a function on what are called the natural variables. And this comes practically from the first law of thermodynamics that you obviously know, that where T is the absolute temperature, S is the entropy, P is the pressure, V is the volume of the system, N is the number of particles, and mu is the chemical potential. So you see that the natural variable with which you express energy are entropy, volume, and number of particles. So let me write this. And that relation, that property, very important property, has this consequence, that this is seen as a function of these extensive variables. They are called extensive because when you double the size of the system, they become double. This is different from intensive variables like temperature and pressure, that if you increase the size of the system, keeping at equilibrium, temperature, pressure, and also chemical potential remain the same. That's why they are called intensive variables. Instead, the energy, as you see, is expressed as a function of only extensive variables. But because of additivity, this will be a function of this form. So the energy will be a function, a linear homogeneous function of the extensive variables. And this means that this property is a consequence of what of this, that if you want this to be, let's say, lambda n. So let's change the size of the system. This will be equal to. And to have this linear homogeneity, the form of the energy must be that one. This property extends to all the other thermodynamic potential that also you know about. For example, the free energy.
So Alessandro, the line of argument goes like this. So it is additive, therefore it has to be of that form.
Of that form, from this you get this.
So this.
Yes, I did. Which is defined like this. Sometimes this is called a Legendre transform, and since from the first law of thermodynamics, okay, no, let's write in the directly with the energy. So when you define the new function like this, I wrote, sorry. So this is a function of n as v, this one. But then what you do is to invert this relation, okay, to get a function of T and V. That means you use this definition to express the energy as a function of entropy, temperature, and volume. You substitute in this relation, and this becomes a function of temperature, number of particles, and volumes. Also, this thermodynamic potential has the same property of this property here, but now, since you see you have an intensive variable here, changing the size of the system means doing studying T, considering the free energy of a system in which you have increase or decrease the number of particles and correspondingly the number of the volume, and this should be equal to lambda here. So also in this case you have the property of linear homogeneity, and as a consequence f will be n function of T b over n. I repeated, this is all stuff that comes from additivity, so it is valid for a short-range system, and everything of this sort will be not valid for a long range. And all the consequences about, for example, ensemble inequivalence come from this, from the failure of these properties. Let me just to mention, because this is important, I just don't want to be repetitive, but this is important for the following, that you have another thermodynamic function, which is the Gibbs free energy, which is defined. So this is another kind of Legendre transform, because F inherits, let's say, this property from the energy. Because if you you can do by exercise. If you start from the differential expression of the energy, you do the first transform, you get the differential equation relation for the free energy. You now do a further Legendre transform, and you get the differential relation for the Gibbs free energy, which is okay. So it is P dV. No, sorry. G will be a function of N, P, and T. So you see, since you have done this Legendre transform, the pressure substitute the volume in the dependence in the independent variable. Then you have this differential relation. Okay. Also, the Gibbs free energy enjoys this property, but now you see there are two intensive variables, temperature and pressure. We are left with only one extensive variable. This implies, because of the additivity property, that there will be a function like this. But now, from here, if you do the derivative with respect to n, you immediately see that this is the chemical potential. Okay? So the Gibbs free energy is the number of particles multiplied by the chemical potential. From this, we obtain a very important property, a relation that, again, will not be satisfied by long-range systems. So let's write dg from that expression. Here we have n d mu plus mu dn. So these two are equal. And from this, you get immediately that St this is called the Gibbs-Duhem relation, and tells you another important fact, which is already embodied here, that these the three intensive variables, chemical potential, pressure, and temperature, are not independent. Are not independent among them. So, for example, the chemical potential is a function of pressure and temperature. So you cannot define a system giving only intensive variable, because so let's take again a macroscopic system which will have a given pressure. So we take as control variables, in this case, pressure and temperature. And this will have a given size. And if you now increase, and mu will be, the chemical potential will be a function of these two intensive variables, or the other two intensive variables. If you increase the size of the system, you keep the same pressure. The other system will have the same pressure and temperature, and the same chemical potential. So you see, you cannot distinguish the size of these two systems given any two of these three variables. You need in some way to give an extensive variable, otherwise you cannot specify the size of the system. I anticipate the fact that, on the other hand, in long-range system, it will generally be possible that these three variables, Pt and mu, are independent, since this relation does not hold anymore. So you can specify, in some cases, the size of the system giving only intensive variables. That sounds a little bit weird if you think to the general system, which are additive, but this is the case.
Just one quick question. So for the long-range systems that you're going to discuss, would it still be true that the average energy is extensive, or there is no such restriction?
The average energy, no, it's not extensive. If you double the size, if you double the, will not be the double. No, that's.
But then somehow you have to demonstrate that you can still get stable macroscopic behavior, right?
Macroscopic behavior, but with different properties. Yes, yes. You will have other relations between the intensive and extensive variables, but still, provided some conditions are satisfied, there will be a macroscopic behavior, and you can define it. And let me give you another.
So when you write G equals to A mu P?
This one?
Yeah.
This one?
Yes. And you substituted small g to
Oh, because so I have this, okay? But now this is the differential equation satisfied by the Gibbs free energy. So if you take from this, if you do the same thing here, you get so G is equal mu. Okay. Then the final property that I want to mention to you, which is satisfied by short-range, by additive system, and very often not satisfied by long-range system, is the positivity of the response function. By response function, we mean generally the second the second order derivative of the thermodynamic potential that give you how tell you how the system responds to an external perturbation. For example, the most typical example is the specific heat. When you change, how is the temperature going to change when you change the temperature of the system? So, for example, this is the typical example that is given. At constant volume. This for additive system is always positive. And it can be seen by exploiting the additivity in this way. That again, if I consider a system and I divide it in two, so here I have a system with energy E1 and V1, E2 and volume V2. And again, I can say that the total energy is E1 plus E2 because it is additive. And, and also the entropy, the total entropy will be S1 plus E2. So let's let's see what the system behaves with respect to perturbation on this separation. So
so the specific heat is positive, so within the canonical.
for short range system, it is positive for always. And it comes from this kind of calculation. So let's do it. Okay. Then I have to consider also a second order. Let me write in a more compact way. This the second. Okay, it is clear. This is the second derivative with respect to the energy.
So you are considering n to be fixed.
Yes. Yes, I think I can take a separation that permits, that can move and can exchange energy, but does not allow particles to go through. Okay. Now, since, of course, dE2 is minus dE1, because the transformation is inside the system, and dV2 is minus dV1. And equilibrium requires S, the total entropy, to be a maximum. Now, I can put equal to 0 before the first order term and after the second order, the first order term, and that's it. And then, but also I have to require that the second order term is such that what I define with the critical points is a maximum. Otherwise, it will not be equilibrium because the entropy wants to be at the maximum. So if I put this equal to 0 with that property, I get that, as we could imagine, the temperature of the two systems are the same, and the pressure of the two systems are the same. So the separation will be in equilibrium. It will be pushed by the same amount from left and from right. So let me see what the other. Now, yes?
What is that ASI EI that second time in the practice hardware?
Here?
Yeah, yes. What are those ASI?
So this is the, not to write twice the same expression, I wrote, this would mean S1 with respect to the second derivative with respect to E1 multiplied by the corresponding differential, and so the others. Then I have to put this second order variation is negative, because as I was saying, the S must be a maximum. So the second order variation must be, let me maybe skip the details, which to be not to, okay, yes, it's better. For example, from when you have a form like this, let's say for any value of x and y, then this is satisfied only if a is negative, and then the other condition would be ab minus ac minus b squared positive. These two together imply also that c is negative, as you see. Because this, in order to be positive, AC must be positive. But if A is negative, AC is positive, only C is negative. Okay? So, apply to that relation, this tells you, okay, I will skip the details. This is just algebraic passages.
So what is the frequency of that? You want that to be, say, x square minus 2bx.
That I have that quadratic form, that I want it to be negative for any value of x and y.
Okay.
And the condition are those two. I mean those three, but one is dependent on the other two. I wrote.
So do you say that given a is 0, negative, what is the condition on the other parameters such that the expression is negative, or
Is this one?
Oh.
You can take this. If you satisfy those two relations, then you are sure that this will be negative for any value of x and y.
And if a is positive?
Then it is not, because you can take y equals 0, then ax squared will be positive if a is positive.
No, sorry, I didn't get it.
You said what happens if a is positive. So if a is positive and you choose y equals 0, then this form reduces to ax squared, and so it is positive. So a must be negative. The same for c, and the same for the determinant of the quadratic form.
So I want that this expression to be negative for all values of y.
And this now x and y are the differential di and dv. So without going to the details that you can work yourself, this means that let me first say that I had to put that separately for each I less than 0. But this, just because of the positivity, extends to the whole system, because I have this homogeneity property. So I can say that the same properties are valid for the entire entropy. So this would be A in that relation. Okay.
Sorry, I missed that part. By calculating equilibrium,
be negative because I'm a function of one dependent variable.
This thing is 0 only at first order. When you go to second order,
You see.
maximum you see.
If I just look at the zero, the derivatives, I could be here and I could be here, but I want to be here. So I have to put that the second derivative is negative. But since is the inverse temperature, if you plug inside, you get this you get from here. From the second relation, that would require some passages, but okay, it is not so difficult. You find that so what is generally defined is isothermal compressibility. Is positive. And you have other bunches of few more response functions like this, which are all positive. And this positivity comes from the property of additivity. You see, I have used only additivity. I have used only practically the physical thing that I have used is that the interaction between the two macroscopic subsystems can be neglected. All the properties come from that physical property, from that physical peculiarity of additive system.
This one, how do you get del V, del P?
Oh, it requires some passage, but I better skip it.
No, you can mention.
Oh.
This one start out, no?
So, okay. So this would be, okay. I have to see. AC minus B square becomes this, okay? But then you see the definition, this becomes the definition of the first derivative. Sorry. Okay, something, yes. Yes. I think so. The S dV is 1 over. Yes. Okay. P over T? So, okay, let me. Here I have, in that case, I have d of dE of 1 over T. Let me write this determinant. Here I have d dB 1 over T. Then I have here d dB pt dV P over T. This determinant is 0, okay? So this is, if you look at it, the definition, this is and the same here. I just inverted the order of the differentiation. So if you multiply these two, you get this, okay? Is it clear?
No, this one is clear. I think he is concerned about your second expression. So you are substituting del S del E equal to 1 over T and del S del E equal to P over T.
Mm-hmm.
That one.
Both of them are equal to this, since P over T is the derivative with respect to V, so EV. 1 over T is the derivative with respect to E, so VE. So if I do the determinant, and this is DE, ds dE, and this is ds dV. And so I get this one, okay? Okay. So this determinant is given by this. Then I have to do some passages in which I have to change the from VE to VT as independent variables, because I want to get this, so VT. And this requires some passages that, because of the time, it's better that you can express this determinant. You see, this is called a Jacobian. This is a Jacobian, okay? You can change these variables in both. This is okay. I'm doing this. Then this would be 1t pt. Generally, the Jacobian is shortly expressed like this. Okay. Now, if you change, if you divide on both by d v 1 over t, v 1 over t. Now you have the ratio of two Jacobians, but you see, since the two variables, the two set of variables, a variable which is coincident, this becomes a single derivative, okay? And both up and down. One of the two derivatives you will find that is always positive because it is t cube, so it is positive, and the other gives you this one, dp dv. So you get that the dp dv must be negative. Okay.
So one question. So you said, if I understood correctly, that some of these response functions can become negative for long range.
Yes.
But I thought the positivity of the response functions was connected to the stability of the equilibrium state.
Yes.
So how do you ensure the stability of the equilibrium state when those things become negative or certain things?
So, for example, let's consider the first response function, the specific heat. So that can become negative, but that can become negative only in the microcanonical ensemble, as we will see. And this does not spoil the stability of the system, since you have to consider a microcanonical ensemble is suited for an isolated system. And the specific heat of a long-range system has to be considered as the specific heat of the whole system. So that means that if you have an isolated system with a given energy, and for a moment you just add some energy, and then remove again the connection, so it will be isolated again. So this system will have a little bit more energy, but if you go to measure the temperature, it will have a smaller temperature. So the stability is not spoiled since the system is still isolated. What the stability that cannot hold in this case is if you keep this system with negative specific heat constantly coupled to a thermal bath. In that case, it cannot be stable. And this is also a very nice physical explanation, because I wanted to say that later, but it is useful that I say that. So, consider a system, and I want to plot the temperature as a function of its energy. So if the specific heat is positive, this means that this curve, whatever it is, has always a positive derivative, since dE over dt or dt over dE must be positive. Consider instead a system which has at least a range of the energies for which there is a negative derivative. In this portion of energy, the specific heat is negative, since this derivative is negative. But now let's see what happens if we couple this isolated system to a thermal bath of a given temperature. So if I couple it to a bath which has this temperature here, okay, doesn't matter. It is okay. Why is that? Because suppose that there is a fluctuation, since the system is coupled, there is a fluctuation, and a little bit of energy goes from the bath to the system. So the system will increase its energy, and will increase its temperature then, because this is positive. So it will. But then, since entropy is such that heat flows always, this is true also for long-range system, from higher to smaller temperature, then this fluctuation will be brought back, because the system has a little bit higher energy than the bath, and will give it back the energy to the bath. The same if the fluctuation is negative. So if the system gives a little bit of energy to the bath because of a fluctuation, its energy will get lower. The temperature of the bath will never change, because it is considered to be very large. So now you will have a lower temperature, so the bath will give it back the energy to the system, because in that case it has a higher temperature. But now let's see what happens here. Now suppose that I have a bath at this temperature, okay? Okay. Now, if the system gives a little bit of energy to the bath, okay, so its energy will decrease, okay, but its temperature will increase, you see, because here this is higher here. But then, if the energy of the system is higher than the energy of the bath, it will be forced to give again energy to the bath. So the situation is not stable, because of a fluctuation, the system has given some energy to the bath. But then it finds itself with a higher temperature and wants to give more energy to the bath. So it will move away from this. This state is unstable. Is unstable, as I said, if the system is coupled to a thermal bath. What is the situation described? The situation which is described, the thermodynamic potential that describes this is the free energy, and the corresponding ensemble is the canonical ensemble. So these states in the canonical ensemble are not stable. In this sense, you lose stability. These states will not exist in a canonical ensemble. And this is already an ensemble inequivalence, because instead they exist if the system is isolated, and the system is isolated when you describe it with the microcanonical ensemble. So these states will not exist in the canonical ensemble, and they exist in the microcanonical ensemble. And this is already ensemble inequivalence seen in this very simple physical way. But there are also mathematical ways to see, still simple, very simple, which more or less are related to a slight generalization of, where was that? To a slight generalization of the Legendre transform, okay? Where was that? Oh, that F equal E minus Ts. We will see that there will be a slight generalization of that transformation from energy to free energy. And this transformation allows to have this kind of differences between canonical and microcanonical.
So you do a Maxwell construction there?
For the canonical, I do Maxwell more or less at the same level. So the system canonical will go like that. And also, something which is different between short additive and non-additive is the following. I can even, doing a correct calculation in a microcanonical setting, get for a short range system something of that kind. But that's because generally when one does the calculation, one considers from the start a homogeneous system, okay? But then what happens physically? If I have a situation like that, then the system says, okay, now I'm here. Here you have a system with a given energy, EA. Here you have the system with a given energy, EB. But as we said, as we have seen, there is additivity. That means that if in each of the two cases, if I cut in two the system, then the system will have still the same total energy, but just EB over 2 in one place and EB over 2 in the other place. But this also here, that I mean, if I'm here and here, what the system finds conveniently, and we will see that when we will see the concavity of the thermodynamic function, that just the system separates in two, but the two phases will be different. For example, one will be liquid and the other will be gaseous. And so, at the end, also in the microcanonical ensemble, you will have a situation like this. So the Maxwell construction that you are forced to do in the canonical ensemble will practically occur also in the microcanonical ensemble by itself. The system will separate in two different phases, which coexist. This also is something that does not occur in long-range system. In long-range system, you cannot have separation of phases. And this also can be understood on physical grounds. Oh, okay. I have closed the loop. Now I have to... Oh, but I can use the same picture here. Okay. So let's take a particle here. It will be, I mean, its physics, its behavior will be determined by its small surrounded within in an additive system, in a surrounding with the range equal more or less to the range of the interaction. The same here. So nothing prevents that these two surroundings are different. This is what happens when you have two phases that coexist. So, for example, if I measure the density in the liquid, it will be much higher than the density in the gas. And there is nothing to prevent this phase separation. Otherwise, in a non-additive system, the surrounding of each particle are the whole system. So I do not expect to have a different, let's say, order parameter, like the density here and here. This is why in long-range system, you do not have phase separation. And going back to that picture, this means that what I was saying before is not possible here. The system has to really jump from here to here in the canonical ensemble, because there is no way to be in equilibrium with two different phases here in this range of energy, like it happens for short-range system. So in these cases, this energy for the canonical ensemble really do not exist. For the short-range system, they exist by dividing the system in two different phases. But since this is not possible for long-range, that energy are really forbidden in the canonical ensemble, and the system has to jump from one energy to the other at that temperature. And this is ensemble inequivalence, since on the other end, In the microcanonical, the system will be, for example, here. Again, also in the microcanonical, you cannot have phase separation, but you can have this energy because there is no but to which you can be stable, unstable to, because you are not giving energy to some but. Okay, so let me, where is it? Oh. Some of these issues I already talked about. So when I said that the thermodynamic potential are a linear homogeneous function for additive system, I also said that this is no more true for a long-range system. Then the Gibbs-Duhem relation is not valid. Instead, we have to see this, why it is that.
For the first point there, so of course for short-range systems, there was a natural way of identifying extensive variables. So when you take a long-range system, how do you identify what the extensive variables are in that first point that you're taking?
Well, more or less is the same. Extensive means that when you, for example, you double the size of the system, they have to change macroscopically, regardless of the interaction, even if short or long.
Volume and number are natural extensive variables, but energy, for example, might not.
Might not, because you say you could have a negative contribution of the interaction, yes, but I think that from the mathematical point of view, you have to consider that extensive, because also the negative contribution can be, I mean, if you increase the size, for example, in a gravitational system or in a plasma, the negative part of the interaction can increase macroscopically when you increase macroscopically the size of the system, although not in a linear way. But still, the temperature, the pressure, and the chemical potential are intensive, since they do not change when you increase the size of the system. I'm losing my voice. Okay. Gibbs-Duhem relation is not valid.
No, so he's asking about the extensive variables.
Yes.
So number and volume are fine, but energy is not extensive, super extensive. So you have to.
No, okay. What I know what you mean. Not extensive because it is not linear. Yes. Now I was answering, considering extensive as something that changes macroscopically. Okay, it is not linear. Then mathematically it is not extensive in that sense, but it is something that changes macroscopically when you change macroscopically your system. That's.
So when you say extensive, do you mean quantities which are linear in the number of particles, or quantities that just increase? Could be linear, could be not.
When I said this is what I wrote at the beginning, that if you take just meant that. Linear homogeneous function, I mean that. When I say this, what I wrote there means that this is not valid. That's all.
And S will be extensive anyways, regardless of
Yes.
whether it is, because it has nothing to do with the range of.
Yes, S will be extensive.
So
Yes.
S P, and then E will be whatever, depending on the.
S is extensive because that's just microscale.
Yes. Okay, the Gibbs-Duhem relation. So let me. Okay. So this is a construction in which we are still in the. Sorry. I take now, consider still be in the framework of thermodynamics, not yet statistical mechanics. But let me consider what I can call an ensemble, but it is not ensemble in the statistical mechanical sense, the way which is used generally. But so consider that we have, for example, this is our macroscopic long-range system with the energy E, S, entropy S, volume, and number of particles. And we consider an ensemble of non-interacting replicas of this system. And so if we consider the energy, entropy, volume, and number of particles of the whole system, since they do not interact, I can say that the total energy, M is the number of replicas.
Yes, so these are non-interacting.
Non-interacting replicas of the long-range system.
Not necessarily, you have to put all of them inside the same box, but this doesn't mean anything.
No, this is just a mental construction.
Oh, mental. Macroscopic replica.
Yes, macroscopically. No, can be also can be two, for example. No, just they do not interact. Then I have B, T, and okay. Now, suppose that we change all these variables, okay?
What is the subscript?
Sorry?
What is the subscript that you have written for E?
Total. I didn't want to use capital T because of the temperature.
It looks like time, so
Okay. Okay, so suppose now we change, you make a change in dst, in dvt, in d and t, and also in the number of replicas, okay? So there will be a change in the total, in the energy of the total number of replicas. So I can write this relation. Then another term that I call here. Okay. This defines this quantity. Okay. Okay. Now, let's see when we take this. That defines the differential as the ST, dBT, and dNT. So suppose that we do. We divide the number of particles of each system by B, the same in the entropy of a single system. Okay, but we also do this. Okay. So this means that dst, dbt, and d and t is equal to 0. Okay. Since I have divided n the particle of this system of a single system by b, but then I have b more replicas, so the sum is 0. The change is 0. The same for the entropy and for the volume. And this implies that d et is equal to epsilon dm. What does that mean? Let's see what happens if the system is instead if it is short range. Okay. So from the additivity, so let's say that and therefore so there should be some, okay. So for additive system, this new thermodynamic potential, I call E, calligraphic E, we use this calligraphic E, is equal to 0, as we expected, because it was never introduced when we studied the additive system in the normal courses. On the other hand, when the system is long range and this relation is not satisfied, this scaling is not satisfied, det, when you do this kind of a transformation, is not necessarily equal to 0, and so E, this calligraphic E that we call replica energy, just because it is related to this kind of mental construction, is not equal to 0. So we are seeing that E equal to 0, replica energy equal to 0, implies non-additivity. Sorry, additivity implies that the replica energy is equal to 0. Therefore, on the other way around, if the replica energy is different from 0, we have non-additivity. And this can happen only in a long-range system. Now, let's see what is the differential expression for this new thermodynamic potential. So, like all the others, it has a natural variable with respect to it is expressed, and a differential relation expressed as a function of this natural variable. So let's write again. Where is it, the relation? No, maybe I need, oh. Yes. Let's use that relation here. Okay. Now suppose that we express that relation keeping all single system properties constant. So we will have this. Okay. No, sorry, the other way around. Okay. Then I will have a relation in which, a differential relation in which the only differential will be dm. Let's apply that relation in the case in which I keep all the single system properties constant. So the total, for example, the total entropy can change only because I change the number of replicas. ST, the total.
Times again. No, there is an M in
So ST will be, this is this one, okay?
No, you have written, okay, that is mod.
Oh.
No, the previous line.
This, yeah, I shouldn't put it here as
SDM.
SDM, yes, sorry.
Okay.
Yes. SDM. Okay. So that I will have sorry, TSDM. And this is the same. Now I can formally integrate for m from 0 to 1, and I get the relation that I finished my chocolate, because that's all downstairs. Okay. If I integrate that relation, which I have a one only differential, dm, then I take everything to one side. I have E plus PV minus mu n minus Ts. Okay, this is the definition for a finite without using a differential properties. This is the replica energy is equal to ET? No, this is for a single system. For a single system. I have formally integrated that ET for m from 0 to 1. I understand that it is something, so I can consider a single system. And from this we can derive now the differential for F. I can write this. First, I write just from here. Okay, but then from here I can use the first law of thermodynamics, which is always valid. This is equal T ds minus P dV plus mu dn. Okay, then there are some simplification. Okay, better that this with this. This got with this and this, so I get I don't know where it is written now, but if you remember, this was without this was the Gibbs-Duhem relation that's saying that this differential form is equal to 0, expressing the fact that mu is a function of T of and P. But now this is no more 0 because it is the differential of this new thermodynamic potential. And this comes again from the fact that additivity does not hold. So the physics is all in that properties. And also, as I was saying some time ago, that with PT and mu, contrary to what occurs for short-range system, you can define the size of the system. While for short-range system, you couldn't, because this had, if you gave, apart from the fact that you can give independently only two of them, but giving two of them does not define the size of the system. You have to say, if here there are n1 particles, and here maybe there are 2 n1 particles. But if you do not say that, you do not, from P and T, you cannot define the size of the system. Here, since they are independent, you can define the size of the system given the 3 independent intensive variables. So if you, for example, if you increase, in that case, for example, if you increase the size of the system, and here, and in that case, it is no more dependent from P and T, and you keep, for example, the same P and T, you do your transformation, keep it the same P and T, this will be different. Will not be the same, contrary to what occurs for the short-range system. That means that given the value of mu, I can determine which is the size of the system.
Alessandro?
Yes?
So I understand that why this fancy epsilon is 0 for short-range system.
Sorry?
So I understand for short-range system why you get back the Gibbs relation, because you have the epsilon to be 0. I mean,
Why you get the Gibbs-Dual relation for a...
No, I get that. I'm asking that why do you not get it back for the long range one?
No, I just worked out what is the differential formula for this from its definition and applying the first law of thermodynamics, making cancellation, I get this. And I discovered that this differential form is exactly the differential form that is equal to 0 for the Gibbs-Dual relation. There is nothing, I mean, coming from some kind of reasoning in this case. It's just a mathematical fact. But the physics is that before it was 0, this relation was 0, meaning this fact that this was a function of P and T. Now it is no more 0, means that you can take P and T and mu independently, since the value of these 3 intensive variables determine this is a function epsilon, replica energy is a function of P, T, and mu, as seen as 3 independent variables, something that was not possible to take for additive system. So you could not define at all the replica energy. And we also found in fact that for an additive system, this is identically 0. So it is not defined. It is not defined.
So I think you are defining a quantity, namely this
Call it replica energy.
replica energy, which allows you to distinguish between short range and long range systems.
Yeah.
This replica
Suppose that you do the...
0 for short range, non-zero for long range. It is constructed in such a way that it becomes non-zero for long range.
Yeah.
Right, I mean, it's by, introspection or something like that, no? Because yeah, because how do you define such a quantity? I mean, replica is kind of unusual.
These are still in thermodynamics, but now we are going to statistical mechanics, and we will see that there is still okay, but still, I mean, suppose that just stay in thermodynamics, you compute this quantity for a given system. Let's do this. This addition of thermodynamic potential. This is epsilon. You see that this is 0 for a short-range system because this is equal to G. We saw it before. But G is equal to E plus PV minus TS. So you have G minus G equals 0. Okay, I have exhausted those points, existence of a new thermodynamic potential, the replica energy, and the fact that PT and mu can be independent, and that you can define the size of the system only. How do you know that? What is the replica energy? So, okay. Generally, I mean, in statistical mechanics, this quantity is computed by doing some kind of partition function. For example, the free energy would be this minus this. You know that you compute it doing the logarithm of the canonical partition function. You can, then in that case, you would also have and also mu, sorry, okay. So if you compute, for example, the canonical partition function, you find the free energy, the pressure, the chemical potential. T and V are already your control variables, so you chose by yourself computing the canonical partition function. So you can do this. You can do this sum, and you compute so you can compute the replica energy.
Since the example I mentioned that with change in the number of particles in the system, the value of the chemical potential is changing. So is it true that the chemical potential in this case is not an intensive variable?
The chemical potential is not an intensive variable. In that case, yes, mathematically it is true. But since when you go to the limit of short range, they become intensive variable. This name is kept, even if mathematically I understand, as before, the objection before, that when it is not linear, mathematically, we do not call it extensive anymore. And when they change, we should not call it intensive anymore. But still, since they are the same kind of physical quantities, both in the long range and in short range, we keep this name, even if in this case from changing the size they change. From quantitatively also you can think that there will not be a change as macroscopic as for the extensive variable when you change the macroscopic size of the system. So from the physical point of view, you can think about that.
It's a more gradual change.
Yes, I think that's the reason why we keep calling them non-intensive variable, even if they change in the size.
So in the recipe Campa, so this replica energy, it seems like it's the difference between the Gibbs free energy and the term mu n, right?
Yeah, this is, you can write this G minus.
Now, since we are dealing with a long range system, so the energy is not extensive in n. So therefore, I would expect that G is also not extensive.
Yeah, that's why it is not.
Okay. So that they don't cancel.
Yeah, they do not cancel. Yes.
It's not linear, so therefore you cannot. So even if you take out the linear part, there is a non-linear part that remains separate.
Yeah.
So why do you call it replica energy? I don't know.
Because the mental construction was doing replicas.
Why do you do that mentally? Why do you do that mental construction?
Because it seemed to us to be, an easy way, as you see, the mathematics is trivial, it's elementary, to get to arrive to this point that this is different from zero. Of course, you can compute it. You can, as I was answering.
Otherwise, it's hard to write a differential formula.
Because unlike a short range where I would have taken a big system and break it up into small parts, I cannot do the same construction.
No, in fact, if you do it, you get which is zero, as I showed to you.
No. I'm saying that suppose I were to define this replica energy differently. One possibility could have been that I take a very long range system and break it up into small parts, but I cannot do it because they will be cross.
They will be interact. Okay. Yes, that's the point. Okay. Okay. I will have to cut some parts of. Okay, so. Well, so when we go to the statistical mechanics, some things that I have said based just on physical consideration can find some mathematical justification. Okay, if I don't get, if I will be late for, doesn't matter because I can anticipate the second lecture will be of some kind of application to a specific model. So it will be less general, not based on principle, but just on application. So if I have to cut something, I will cut that. But it is better to go over the principles, I think, at least. Okay, so now to see what happens. So let's start with the definition of the canonical ensemble. I have what is called the partition function of the canonical ensemble, as we said, function of as the entropy, function of the energy, the volume, and the number of particles. This, as we know, for example, for a classical system, you all know this, of course. Okay, this practically is the number of states in an energy shell between E and E plus delta. That's, let me put an index here. That fortunately then at the end when you do the calculation does not depend on delta what you find. And okay, let me also write the corresponding quantum. With the usual bracket or ket bra notation. Okay. Yes. This is also can be written doing expanding. For a small delta, you can write this as a okay. Okay. So this is the usual definition. This is valid for a short, long-range system. This is a definition of the partition function in the microcanonical ensemble in which the system is isolated. It has an energy E, volume B, and number of particles N. Then the important thing that will apply also to the other thermodynamic function, the other ensembles, can be seen already just going to the second ensemble that is generally considered when we study statistical mechanics, which is the canonical ensemble, okay? Then we have now an ensemble, let me C for canonical, which is now a function of not more on energy, but on temperature, but still as a function, is a function of volume and temperature. And in the classical case, is this one. Okay. Okay, in the quantum case, would be just the sum over all the energy eigenvalues. Sorry, not all the energy eigenvalues, all the states, because they could be the generators, of course. And in between the ket and bra, you have E2 minus beta En. Okay. Okay, but what is important for our purposes is to write this in a way in which, using the definition of the delta function, I can arrive easily to this okay. So I have replaced the integration. You can put a delta here and add the integration over E over delta. Then perform the integral over the phase space of the system D3NP, D3NQ. You get this, and then you remain with this factor. But now you can also make this change again. From the definition of the entropy, you can write this. Okay, I just substituted omega delta with this definition in terms of the entropy. Now, and this is the key point in all calculation practically that one does with practical cases, practical models, concrete models. Most often, I'm not saying all the time, so most often you exploit the following fact, that you are making an integral over very large quantities, because this, S is the entropy of the total system, E is the energy of the total system. So regardless of the size of the interaction, these are macroscopic quantities. Okay? So after I do the definition that F, and it is not difficult to see that this is a sensible definition. Oh, sorry that I forgot to say that, no, maybe it is time to tell it now that I'm taking units in which the Boltzmann constant is equal to 1, just to avoid to write it any time. That's why this is, that should be dimensionally put divided by KB, but I put KB equal to 1. Okay. So here, it means that this is equal to E. Okay. But then I have that is that one. But then, as probably you have used in other issues, in other arguments, other subjects, since it is a common mathematical property, you use what is called the saddle point approximation, Laplace, I don't know, sometimes it is the name of the Laplace, and that means that you substitute the value of the integral with just the value of the maximum of the exponent. Just because being a macroscopic quantity, this means that the exponent, it has a very large peak. Sorry, E to this very large quantity has a very large peak. Or if it has not a peak, there is a point in which it is macroscopically much larger than for the rest of the range of integration. That means that at the end you can write that sorry, 1 over t. If you apply this to this integral, you take the minimum with respect to e of you see the difference with what I was saying, that we need to take a slight generalization of the Legendre transform. Before we had just like that, without taking any minimum, with beta equal ds over dE. But that's because the property of the thermodynamic potential, in which the positivity of the response function of the thermodynamic potential require that the thermodynamic potential are concave function, where concave means like that. So if they have a double differentiable, means that the second derivative is negative. Otherwise, there is a more general definition that is valid also when the derivatives are not defined everywhere. So when you have this property, this is, when you plug here, is uniquely invertible. This is not the case if S is not like that. If this is S, for example. This is not concave. Okay, let's put it always increasing, but not concave. This is not uniquely invertible. So you have to define another way. And that you obtain directly from the definition of the canonical function as a function of an integral of the entropy. And also from here, you can derive the inequivalence of ensemble. So from a very different route from the physical point that we saw before. And it is a simple, also in this case, it is a simple mathematical fact. So we said that graphically concave functions have function which, when they are double differentiable, have a negative second derivative. But more generally, without invoking the continuity of the derivative, you have that a function of x is called to be concave when you have that. Take two point in its range of definition. Okay, and then take any point in between, and you can define any point in between vary between 0 and 1 a number c in this way. You see, if you choose a c between 0 and 1, you can explore all the range between x1 and x2. If the function is concave when this is larger or equal to c f of x1 plus 1 minus c f of x2. In fact, the right-hand side defines this. Okay, if you take this f x1 and this is f x2, if you vary c, you run along this straight line. And you see that when the function is concave, this is smaller than the function here, because this defines the function at any point in between. So this is the definition of concavity when the derivatives are not necessarily continuous. Maybe you can have a jump in the derivative here, a discontinuity here, a kink, but this is still valid, while you cannot use the definition of second derivative negative when not even the first is defined. Okay, The important thing mathematically is that regardless, if we define now what is called you see the relation with this expression, what is called the Legendre-Frenkel transform, which is a generalization of the Legendre transform, in which you define, taking a function f, you define the function of x, you define a function of y, taking a minimum of this, a minimum in x of this function. Okay? So, yes? Sorry?
Time is almost over.
Oh, okay.
More than
Yeah.
over.
Okay, I will finish with this. You can do it, work out yourself. You can prove very, very easily that regardless of x can be concave, not concave, convex. Regardless of that, g of y satisfies this. So g of y is concave. See, this is very important. That means that regardless of S, if S is convex or are convex portions, this is always concave. And again, this, if you see the consequences of this, you will see that even if the isolated system has a negative heat capacity, when you put it in contact with the thermal bath, it will always have a positive heat capacity. That also means that since, as we saw before, there are portions in which it is not stable where it is coupled to a thermal bath, those ranges of energy will be prohibited. But the concavity of this, regardless of this, means that, as you can prove in other way, looking at the definition of the canonical ensemble, the specific heat in the canonical ensemble is always positive, regardless of what happens in the microcanonical case. And this, so when you have a negative heat capacity in the microcanonical case, you have ensemble inequivalence, because there will be energies for which the system is not stable when put in contact with the thermal bath. So there will be energy which are prohibited. As we saw when you do the Maxwell construction, the system has to jump. That means that this range of energy in the canonical ensemble are forbidden, while in the microcanonical can easily come in. Since the system is isolated, nothing prevents the system to have those energies. This extended to the other, okay, so I have to stop here and let me see what I can do. Okay, so I will cut, as I was saying, I will cut on the applications, but I will finish on the principle. By the way, are almost done. And but at least we have arrived to ensemble inequivalence and negative response function. Then we will see how the replica energy is related. We have seen that the free energy is related to canonical ensemble. The Gibbs free energy is related to another ensemble, which is called isothermal isobaric. Then we have the grand potential, which is related to another ensemble, which is the grand canonical ensemble. We will see that there will be a new ensemble that we have called unconstrained ensemble, which is related to the replica energy. And this will be the end, more or less, of the part of principles. Then if I have no time, I will do just a little bit about application, but that will be just application. I mean, the most important part will be the part of the principle. That I hope that I've given the flavor how you can derive in a very simple physical terms the fact that long term gives you a lot of different properties from long range from short term, and also the fact that mathematics behind this is very simple. You see, there is not much more than this Legendre-Frenkel transform and the properties embodied in that transform. More or less, all of the difference between short range and long range are in this. Okay, so sorry to have gone there.